Okay, so thank you and welcome to everybody. I'm really a co-organizer only in name. All the work has been done by Sujay. So this workshop was is a response to some recent developments in fields across mathematics and physics. So this talk is meant to be an invitation to the subject for non-experts, and it's also meant to lay out some basic definitions and intuitions for the other speakers, so that they don't have to spend time on that. So there'll not be anything very new here. So what I'll do is the first half of the talk I'll just go back to really old stuff, talk about just modular forms and Jacobi forms and what they have to do in, with respect to physics, how they appear in physics. And the second half I'll talk a little bit about the new things, namely the mock-modular forms and mock-Jacobi forms. So, so as Sujay said, this is also meant for the students and local participants. If something is not clear, please ask questions in my talk, but also in every other talk. Okay, so let's begin with just classical modular forms. Of course, this doesn't work. So what are modular forms? Well, the definition is the following. So a modular form is a holomorphic function f of tau. Tau is in the complex upper half plane, such that under modular transformations here means SL to Z, which act on tau as fractional linear transformations, a tau plus b over c tau plus d. F of the transformed variable is equal to f of tau times a factor which is c tau plus d to the power k. So k can be either integer or half integer. That's the most common appearances that we'll see. If k is 0, then this is called a modular function. That's just invariant under the modular group. Unfortunately, there are very few examples. In fact, all the examples are generated by one function called the J function, which we will meet very soon. So that's why one also allows for this kind of covariance property. And once you have this, there's a very rich theory. And this k is called the weight of the modular form. Now, from the definition, it's clear that if you have two modular forms of the same weight, their sum is also a modular form. And if you have two modular forms, their product is also a modular form whose weight is the sum of the two weights. So there's a ring structure. Now, if you take A, B, C, D equal to 1, 1, 0, 1, then this equation implies a periodicity for f with period 1, and therefore you can write a Fourier series for f as follows: f of tau is equal to sum of a of n times q to the n, where q is e to the 2 pi I tau. So n runs over the integers, and one can be more precise as to what exactly n runs over, and that depends on certain analyticity conditions that one has to put on f. But I'm going to gloss over it unless there are questions. Now, in most so these numbers a of n are rational numbers, and you can normalize it in such a way that they are integers. And in most applications, it's these integers that are interesting. So these numbers a of n typically turn out to be the solutions to some problem, some interesting problem, either in physics or mathematics that we have. So the modular form, what it does is somehow summarizes the answers into some nice function which has some nice symmetry properties. So let's look at some examples. So the basic examples are what are called Eisenstein series, defined for every even integer greater than 4. You can also do it for 2, but that's not modular. In the definition, I have not written it down, but it's fairly obvious from the formulas. You normalize it such that it begins with 1, and there are only positive powers of q. These numbers are 4 times the 2 times k divided by the Bernoulli number. 4 times k divided by the Bernoulli number of 2k. So it's some calculable object, and here there's an explicit formula. You can now expand this algebraic expression, and you'll get what is the Fourier coefficient of q to the n, and you will find that that is equal to the what are called divisor sums. So for every n, you look at all the divisors of n, raise it to 2k minus 1 power and sum them up, and that is the coefficient that times this Bernoulli number. So I have not written the formula for 2k, but it's fairly obvious what it is. Now the next thing I'm going to say is something very important, at least from the point of view of applications. And the point is why, I mean, what's the big deal about modular forms? Suppose you find some modular form in some application of yours. The point is that the space of modular forms of a given weight is finite dimensional. So such statements have to be qualified as to what exactly I mean by space. As I said, I won't do this, but this statement in spirit is always true. So whenever you have some automorphic property, either the one I showed you or something larger or smaller, turns out that the space, the ring as we saw, is finitely generated. And that gives us a lot of power, because suppose we have some equation and we know that both sides of the equation obeys the same modular property, then you know that the space is finite dimensional, so you can write down some explicit basis, and then if you want to verify this equation, if you want to prove this equation, you just have to verify that a finite number of coefficients agree on both sides, right? So that's the big power of modular symmetry. Yes?
So finite dimensional, you imply finite dimensional as a vector space?
As a ring. So yeah. So
generated by finite number.
Yeah, so you can see an example here, right? So this is the famous discriminant function. It's eta to the 24, Dedekind eta to the 24, whose coefficients are what are called Ramanujan tau functions. And this has this is a modular form of weight 12. We already saw E4 and E6 of weights 4 and 6. So E4 cubed and E6 square also have weight 12. And the space, the dimension of the ring at weight 12 is equal to 2. And here we have 3 functions, so there must be one linear relation. And you can just ask what is the relation, you get these coefficients. Okay. So because of that, you suddenly get an infinite number of identities, because as we saw, the coefficients of this has to do with some divisor sum with power 3, here with power 5, and you just expand it and you get some, for each n you just match the power of q, the coefficient of power of q, and you get for free an infinite number of identities. So that's the power of modular symmetry. Okay, so here's another example. So there's a function called the J function. One way to think about it is that it comes from lattice theories, the partition function of the Leech lattice, which is the unique 24-dimensional even self-dual lattice. This is a complicated way of describing the J function, but that's one way of doing so. So you compute this function, you get this expansion q inverse plus 24 plus 196884 q plus so on. This has weight 0, it's a modular function, and in fact this is not holomorphic because it blows up at I infinity, but you can multiply this by delta. Delta begins with q, and you'll get a holomorphic function of weight 12, and again you use the same principle. So there are 3 functions, j times delta, e4 cubed and e6 square, and you can ask what is the linear relation between them. In fact, I did this yesterday, and there's some 7 and 5, right? So again, so it's very easy to prove results of the following type if you know that objects are modular. Okay, so one reason I picked this example is because of this identity 196884 is equal to 1 plus 196883. So if there are any finite group theorists in the audience, you'll recognize that this number is the dimension of the first non-trivial representation of the monster group, and you'll see more of these in other talks in the conference. Actually, I'm not sure Kazuhiro is going to talk about this or not. So sorry. So I thought, excuse me. So okay. So that's sort of a brief overview of what modular forms are and why there's so much power. So there's a full theory of these, and I refer you to. There are many good references. But now let's go on. Yeah. So in fact, the holomorphic modular forms is freely generated by E4 and E6. That's the theorem.
But in general,
yeah. So more general. So the answer to your question will depend on the specific example. We'll see later. For instance, Jacobi forms. So the even Jacobi forms is freely generated by two objects, by two functions, and the odd ones are generated by three, but with one relation. So that depends on, there's no unique answer to that. Okay. So now let's ask where do these modular forms appear in physics? Okay. So they appear in many places, and I'm just going to sort of pick a few examples, a couple of examples, mainly because these are the examples which we will talk about during the workshop. So the first relation comes because of what I already mentioned, namely that modular forms are generating functions of solutions to certain interesting counting problems. So these coefficients A of n often are answers to some question that you can ask in physics or combinatorics. So I see there are quite a few string theories here. So let's take an example from that. This should be familiar. So consider heterotic string theory which has 16 supersymmetries, and you ask yourself the question, how many half BPS states are there? So half BPS means states which preserve 8 out of the 16 supercharges, and you ask at a given mass square equal to n minus 1, how many states are there? Okay. So that's a very well defined question. And because these things are supersymmetric, the mass square is equal to the charge square. And this question was answered by Dabholkar and Jeff Harvey, and they said that well, all these states actually take the form of just a fundamental heterotic string. So when the string coupling is very weak, the left and the right movers are decoupled, and because so supersymmetry tells you that the right mover should be put in the ground state, and that will ensure this condition, and then all you have to do is to excite the left movers with some oscillator number n, and then the question simply becomes how many ways are there to distribute the number n into 24 oscillators. 24 is the number of is the field spectrum of the left moving heterotic string, and that answer is very easy. We've all seen it. It's just a partition problem, and the answer, the generating function, sorry, this d micro should be exactly this d, I meant d micro. The generating function is 1 over eta to the 24, the Dedekind eta to the 24, which is 1 over delta, the function that we just saw. Okay, so this is a modular form of weight minus 12, and here is its Q expansion. It's very easy to compute these numbers. So that's one kind of problem where modular forms appear. So this has lots of generalizations. Many such problems of counting BPS states in string theory have answers, the generating functions, which are summarized by some kind of automorphic form, either modular forms or later we'll see Jacobi forms and so on. So that's one part of it, but in fact there's a deeper reason why these counting problems are interesting in string theory, and the reason is that in string theory, if you take a fundamental string and excite it, suppose you take n to be very large, then in a certain regime of parameter space you get a black hole. So the point is that in string theory you have a parameter called G string, which you can tune in supersymmetric theories, and that's the string coupling constant, and when it's very small compared to 1 over n, the picture is exactly what we just saw. It's just some free string which is oscillating. Here I've shown some more general configuration with d branes, and then you just have to, you can do this kind of partition problem that we just did and count how many states there are. But when you tune G string to be large, then G string, being the strength of the string coupling, actually controls the gravitational coupling constant, and so when G becomes large, the Schwarzschild radius of any object becomes large, and once it becomes larger than the Compton wavelength, you get a black hole. So for large values of G, the correct description is in terms of some effective Einstein theory coupled to matter fields, whose solution is given by a black hole. So here I've shown that with the same energy or mass as we began with. Right? So here I'm talking about supersymmetric situations, so one expects that the number of states, at least naively, does not change when you change these change the moduli. So this picture is very nice, and the reason it's even nicer than it might look is because in this part of the picture, one actually has a different kind of understanding of the physics. As I said, there is that's described by Einstein theory, and you can ask here you can count the number of states. You can say, how do I see that here? Well, this the answer to this question relates to some work of Bekenstein and Hawking, very famous work, who said that black holes have thermodynamic entropy, and this thermodynamic entropy, at least classically, is measured by some geometric quantity. So you have some black hole solution, so you just measure the area of its event horizon, divide that by 4 in Planck units, and you can measure what is the thermodynamic entropy. And because you expect that the number of states doesn't change, this thermodynamic entropy should be just equal to the log of the statistical entropy of the microscopic situation. Here we've already counted how many states there are. This d micro, this is a coefficient of this modular form. So if you want to ask whether these two agree, what you have to do is to do a large charge estimate for d micro. That's very easy to do because we know what the generating function is. You can just do a saddle point approximation to get this exponential behavior. So this was done in the mid 90s by Sen and Strominge and Waffa in an example with d-branes, and one finds indeed that the log of the microscopic degeneracy is equal to the thermodynamic entropy. So again, I'm glossing over a few points, but that's roughly the spirit. But the point is now one can do much better. So if you, for a generic function, suppose, so here in the example I showed you had a 1 over delta, you could always do a saddle point approximation, but the fact that 1 over delta has a modular property means that you can do much better and compute these dots to arbitrary accuracy. So this is called the Hardy-Ramanujan-Rademacher expansion, and one can actually find analytic formulas for d micro as a function of n. It's perfectly convergent analytic formulas for d micro. So again, I won't discuss this very much, but this I'm happy to take questions later.
Coming from modular functions.
So any modular form. So in this case, in our case, we had some 1 over delta. So 1 over delta, but in general, any modular form, if you write this as d of n q to the n, there's a formula for what, in this case, for instance, d of n is equal to sum of some Bessel function. I don't remember the index, the sum index here, times 4 pi square root of n times, sorry, yeah, times some Klosterman, something called the Klosterman sum. Okay, so it's a very explicit formula. Everything is known, and you can see that for large n, the Bessel function begins as the exponential, and that's what you see here, right? But in fact, you can do much better. Okay. So that's a completely explicit formula. You could do this for any function by the saddle point approximation, but here you have a convergent analytic formula for d of n, and for that you need modular invariance. And that's what. So most of this was actually worked out by Hardy and Ramanujan, and then this was completed by Rademacher. Okay, so let's go on. So this we saw that. So one instance where modular forms appear in physics is solutions to counting problems, and in this case they can be a very useful guide to other aspects of physics, in this case quantum gravity. So for instance, this is one of the only situations where one has such good formulas, controllable formulas in quantum gravity, right? So it's extremely powerful. And then once one has these things, you can ask, how should I interpret them in the gravitational theory, and that's a whole different research field, and there's been some progress on that front. So one can now ask, well, all this is good, but do we really understand why there is a modular invariance at all, right? So in this case I said the answer is a modular form, but why is there a modular symmetry at all? And the answer is that sometimes we know why there is, sometimes we don't, and in this case we actually do, and the answer is because the vibration of a string is governed by a two-dimensional conformal field theory, as you learn in your first string theory course or first reading course. And so you can think of these counting functions as partition functions of this two-dimensional conformal field theory on a torus, okay? Which has some modular parameter tau, and the modular transformations are then simply just large coordinate transformations of the torus. So this is the symmetry of the problem. So think of it as some two-dimensional theory living, some conformal field theory living on some two-dimensional surface, which has some symmetry. So it's a symmetry of space-time that should be reflected in all the observables, and therefore any computation you do in this conformal field theory should reflect the modular symmetry. Okay, so this is true for if you just take a free boson on a torus, you'll find some answer which is a modular function, but it's not holomorphic. So in order to get holomorphic functions, one has to look at supersymmetric theories. So let's look at n equal to 2,2 superconformal field theories. So what that means is that there's an infinite dimensional algebra with lots of currents, left and right moving currents, and the important charges for us are these three. So there's the Hamiltonian L0, there are two supercharges Q0 plus or minus, and there's a U1 R current J0, and this is a Z2 charge as well, which is the fermion number -1 to the f. And one writes something like a partition function. It's called the elliptic genus, which is a function of the theory, which I call M, and two parameters tau and z. Tau is in the upper half plane as before, and z is a complex number. So it's like a partition function. It's a trace over the Hilbert space times q to the L0 q bar to the L0 tilde. Tilde always means right movers. But it's not quite that. I do something slightly more refined. I stick in a -1 to the f times -1 to the f tilde, and also a zeta to the j0. Zeta is e to the 2 pi I z. Okay, so this is called the elliptic genus of this superconformal field theory. And the reason this is a nice object is because this is holomorphic in tau and z. So by construction it's holomorphic in z, but in fact it's also holomorphic in tau, and the argument is as follows. So look at the basic supersymmetry algebra. Q plus Q minus commutes to L0, anti-commutes to L0, and look at representations of this algebra. So firstly, these two are Hermitian conjugates, so L0 is always non-negative. When L0 is strictly positive, you will find that the representations is at least two-dimensional. So the representations come in pairs with equal value of L0 and opposite values of -1 to the f. So there's always a boson and fermion. That's what supersymmetry means. But in fact, L0 when L0 is equal to 0, then you can have singlets. So you have short representations. In this case, you can have just pure bosons or pure fermions. So this is just some example. You see there's 1 1, 2 2, 1 1, and so on. But at L0 equal to 0, there are two bosons and no fermions. Okay. So now you apply this argument to the right movers, L0 tilde here, and what you see is that suppose you go to a point where the theory, the left and right movers decouple. It's easier to think at such a point. And then the traces are essentially independent traces. So look at the right moving trace. There's q bar to the L0 tilde times -1 to the f tilde and nothing else. But for whenever L0 tilde is greater than 0, there are two states which contribute to that with opposite values of -1 to the f. So there's no contribution. So that means that this object is independent of tau bar. So this means that this is holomorphic in tau. So this is the this argument goes back to Witten, and this is used again and again. So what we find is some holomorphic function of tau and z. Okay, any questions? Okay, however, there's a subtlety in this argument which I shall not talk about, because Jan Trost will talk about this this afternoon, and the subtlety was clarified in the last 2 years, maybe 3 years, by Jan and in collaboration with Suje, as well as Toru Eguchi and Yuji Sugawara, who's also here. So if you want to understand that, come to this afternoon's talk. So now you can ask, so for now, for here, let's just keep, let's ignore the subtlety and consider theories where everything is holomorphic. Now that subtlety happens only in specific theories. so let's come back to this. You have some function of tau and z, so you can ask what are its modular properties. So this leads us to the notion of Jacobi forms. So let's talk about that. Let me pause for questions. I hope I'm not going too fast. Okay. So if I'm going too slow, I'm sorry, but I will do that. Okay, so let's move to Jacobi forms. So a Jacobi form is sort of the next level of an automorphic form. We saw modular forms of one variable. Now we have Jacobi forms of two variables. So one of the variables tau lives in the upper half plane, and z lives in the complex plane. And a Jacobi form here is holomorphic in both these variables. And it obeys two properties. There's one modular property where tau goes to a tau plus b over c tau plus d as before, and z also goes to z over c tau plus d, and that is equal to phi times some prefactors as before. So again, there's a number k called the weight. But there's another property, namely that you can translate z by integer multiples of tau and 1, and under that phi is also almost invariant. It's covariant, and that property is governed by another number called m, which is called the index. Okay, so there are modular forms had one sort of number which parameterized them. Now there are two of them. So again, k and m for us will typically be integers or half integers.
Okay. Z over there, it's Z2, right?
Oh, sorry, that should be yeah. That's excuse me. That's each of them is just an integer. These are integer multiples of tau and z. It's a LaTeX error. So they're just z, the integers. Thanks. Okay, so as before, now there is periodicity in both tau and z. You can easily see that, and so there's a double Fourier expansion. So phi of tau z is sum over n of r, n and r, c n r times q to the n, zeta to the r. And as before, it's these numbers c of n r that are interesting in physics. They come as the solution to some problem, exactly like before. So again, you can put some growth conditions. This is some technical condition to be more specific, so that you can actually write down correct theorems. So the one I will use is here. That's the one which is used, which appears in physics most often. Okay, so now the next point is so far we talked about modular forms. Now I'm talking about Jacobi forms, which are two variable objects. So what is the relation between these two? Well, the relation is as follows. This elliptic property is, I should write this down because this appears again and again. So that property actually implies that all the z dependence of the function can actually be collected in a canonical function called the theta function. So most of us have seen this at index m. So that's the definition, and you can factor the z dependence out into some explicit canonical theta function, and what you're left with is a bunch of functions of one variable called hl. And in fact, there's a finite number of them. There's 2m of them. Okay, you can invert. So this is called the theta expansion. So phi is equal to sum L modulo 2m hl of tau times theta ml of tau comma z. You can invert this relation as follows to compute hl in terms of phi. That's easy. And the statement is that if phi is Jacobi, then HL is modular. Okay, so that's, as you would expect, the z dependence you've collected in some canonical theta function, which are Jacobi forms, and what you're left with is a bunch of modular forms. Okay, so to be more precise, there's 2m of them. So you write a vector, and they're what is called a vector valued modular form, namely that as a vector they transform under SL to Z, they can transform into each other as well with some finite dimensional matrix. So that's the relation. So a Jacobi form essentially is the same as a vector of modular forms. So you can go back and forth depending on what is convenient. So here are some examples. So we've seen many of these functions in, at least in string theory and conformal field theory. So the labels are the weight and the index. So this means that it's weight minus 2 and index 1. So this is the odd Jacobi theta function. This theta 1 square over eta to the 6, and you can write some Fourier expansion in 2 variables. So I've written the Q expansion, and I've summarized the zeta expansion as some polynomials, but you can also write the Fourier expansion. So that has a 0 as z equal to 0. Another example is at weight phi 0 1, weight 0 and index 1, which is we can build using the other 3 Jacobi theta functions. That's the odd one, and then this the other 3. That's some Fourier expansion. The third one is phi minus 1 comma 2, so weight minus 1 index 2, also built using the odd Jacobi theta function, but now with argument 2z over eta cube, and it has some Q expansion. Yeah.
I think there's a factor of 4 in the definition of
Here.
4 times that? Because at 0 it should
Let's see. So at 0 it should be 12. So indeed that's 3. Thank you. So there's a 4 missing here. Thank you. So here there should be a 4. So why do I give these 3 examples? Exactly like so as was the question was asked before. Exactly like for modular forms, the ring of Jacobi forms is also finitely generated, and in fact it's finitely generated by these 3 functions. Okay, so that's all you need to know. These are your basis functions. You put them on your computer. Next time you get some Jacobi form, you just ask what is the weight and index. There's some basis built out of these, so monomials in these times some modular forms, and then you just have to prove equations. You just have to compute some finite number of coefficients. Okay, so this is generated by A, B, and C. Let's call them A, B, and C, but there's one relation between them. So as an example, so you take the elliptic genus of some manifold. So if you take the elliptic genus of the K3 manifold, that happens to be of weight 0 and index 1. So that means that it has to be exactly a multiple of this, because that's one dimensional, and in fact it's equal to 2 times phi 0 1 if I write this correctly with a 4 here. Right.
So the ring is generated by ABC over the ring of
modular forms, or holomorphic modular forms. Thank you. Okay, so that concludes my review of classical modular forms. So modular forms and Jacobi forms and some appearances in physics. Okay, so let me pause for questions. Is there any? So any type of questions, either philosophical or technical.
So here it's crucial to assume analyticity in Z, right?
That's right. So here there was Z was holomorphic. Phi was holomorphic in Z. Okay, so that's going to hit us very soon, as you know. So what is new? So now I'm going to move to the second part of the talk, and this is where mock-modular forms come in. So far I just tried to give you a flavor of like what modular forms are, why they're useful, and where they appear in physics. So let's see what is new. So mock-modular forms.
There are many other places where they're doing physics.
Absolutely. So that's how I began when I said that. So in fact, this was the original, the first quote that you saw. I take it to mean that somehow modular forms just appear everywhere, and so I choose to focus on these 2 places because well, it's important for many of the talks in this workshop, but certainly they appear in many places, and not just this type of modular forms, more generally automorphic forms. Okay, and in general that's the power. If you know there's some automorphy, then you certainly get a lot of power. You can get exact results. Okay, so what is new? The new part appears. The new part has to do with mock-modular forms. So these are functions which, well, so I think all of you know the history. The history is that Ramanujan, in his last letter to Hardy, writes just before he died, writes in a very excited way that dear Hardy, I found some new examples of new types of functions which I call mock-modular forms, because they're like modular forms, they're almost like modular forms but not quite. And then he proceeds to give a list of 17 examples without giving a definition. And then in the 90 years since then, there were other examples which were added to this list, and some progress about what it means, but only in 2002 was progress really made by work of Sanders Weigers, who gave a correct definition, and this included all of Ramanujan's examples, and also this led to a lot of new work, initially a lot due to Brinkman and Ono and Zagier, and now by many other people. So that's the history, and recently we've also seen many appearances in physics, and the story of mock-modular forms even mathematically is not complete. So there's no classification theorem of the type that I showed you. So it's very interesting to understand every new example that appears, and throughout this workshop we'll see at least a few instances where they appear, and what I will talk about now is one such instance. So let's go back to this picture of black holes that I presented. So you have some microscopic theory, which is some excitation of strings and branes, and you can ask what are the number of BPS states. These are summarized, they are generated by modular forms, and the picture so far was that at strong, so these are weak coupling. At strong coupling, what happens is that they all gravitate to become a black hole. However, you can ask yourself the question, sorry, this n should be q comma p. This is a small. So in this case, I've become slightly more detailed, and suppose there are electric and magnetic charges q and p. It's still sketchy, but a little more detailed. You can ask yourself the question, in the gravitational theory, is this the only solution allowed with these charges? Okay. So the answer is no. In fact, we know of other solutions due to the work of Denef and Moore and others. So one type of solutions that we know exist are called multi-center black holes. So these are dionic black holes with electric and magnetic charges, and here you have electric black holes and magnetic black holes with some angular momentum which binds them. And you can ask now, when do these solutions appear and when do those solutions appear? It turns out that the single center black hole appears always, and these things either appear or not depending on boundary conditions that you put on the theory. Sorry?
There are only two types of.
No, so in general, in fact, there are multi-centered black holes. There can be anything. So this is still schematic, but let me answer that again in a few minutes. So you can ask when do these solutions appear? Well, so they appear when, depending on the boundary conditions, right? So when the boundary conditions, so some set of boundary conditions allow for such solutions and some don't, and these the difference between these two is given by a codimension 1 surface in the space of boundary conditions, across which now this is a jump in physics, right? So you ask what is the entropy? Here is the entropy of this black hole. Here is the entropy of this black hole plus the entropy of this multi-center black hole. Okay, so there's some jump. There's a phase transition, and if you're interested in black hole physics, if you want to,
So it's not true that the entropies adds up.
no. So but what? Right. So but I'm saying that if you just look at the entropy, there's entropy here and entropy here. So clearly this configuration is different from this. There's something discretely different, and you're right, of course, and we'll see what happens very soon.
Where are the boundary conditions?
So this counting problem is in 4. So to be explicit, let's take 4-dimensional string theory. I'll show you an example. So 4-dimensional means take heterotic theory, the one that I just showed you, compactified on a 6 torus. So you have 4-dimensional flat space, and there you put the boundary conditions at asymptotic infinity, and you ask what are the gravitational solutions. So it's with, yeah. Oh, so wait, I was going to make a point. So the point is, suppose you're interested only in the black hole, and you ask how many states are associated with only the black hole, then you have to throw out some solutions. But that means that you're destroying the symmetries of the theory, right? You're just throwing out part of the spectrum, and in particular it means that you're destroying the modular symmetry. So that's a big problem, because till now I was telling you that it's the modular symmetry that's a good guide, it helps you solve this problem of quantum gravity. So a concrete realization comes in n equal to 4 string theory, where the microscopic counting function is the partition function of 1/4 BPS objects. These have both electric and magnetic charges. The other example we saw was 1/2 BPS states. This is more complicated, and but this has been solved due to the work of many people. And the answer is that the partition function is a function of 3 variables, tau, z, and sigma. So far we saw 1 and 2 variables, and this is a function of 3 variables, and it's equal to the inverse of a function, a famous function called the Igusa-Cusp form. So I won't describe this very much. The definition is that it's the unique weight 10 Siegel modular form. If that doesn't make sense, it's okay, because I'm not going to use any property beyond the fact, beyond 2 facts. So the first property is that this has some higher automorphic group, and you can do an expansion in the third variable sigma, like so, near sigma equal to I infinity. So you have sum over m psi m tau z times e to the 2 pi I m sigma, and these coefficients are Jacobi forms. So that's what the fact that this is a Siegel form tells you. They are Jacobi forms of weight -10 and index m. The other piece of information we need is that this object has zeros or divisors in the Siegel upper half plane, that is the plane where these guys live. What that means is that if this has a 0, 1 over that has a pole, so psi m are meromorphic Jacobi forms. So meromorphic means now it has poles in Z. Okay, and so the question for ourselves is what is the Fourier expansion? Okay, so can we write such a Fourier expansion? As we all know, meromorphic functions, there's an issue with writing a Fourier expansion. So this kind of Siegel functions and meromorphic Jacobi forms will appear in other talks, I think. But now let's make some precise questions.
So here for fixed tau and z, it also has poles in sigma, right?
That's right. So here I've already chosen to go near sigma equal to I infinity and make this expansion.
The expansion is not convergent.
That's right. So this is a certain, that's right. I mean, it's a power series. It's a okay. So you could ask the same question in the full 3 variable problem, but this is much simpler. Thank you. So the questions we set ourselves are the following. So what is the correct expansion of the meromorphic Jacobi form? From this, can we somehow extract the degeneracies of the single-centered black hole? So as we saw, you have some meromorphic Jacobi form that contains both the single-centered black hole as well as 2-centered black hole. And in fact, to answer the earlier question better, the spectrum of the n equal to 4 string theory actually contains other gravitational solutions with more than 2 centers, but you can prove that to the BPS index that we are counting is only these solutions that contribute, either single-centered or 2-centered black holes. So that's why only these things are important. And thirdly, suppose you can do that. So you have some microscopic formula, and out of that I want to extract only part of it and say this belongs to the single-centered black hole. The question is what are the modular properties? And the answer has to do with Mock-modular forms. That's why that's how Mock-modular forms appear in this context. So I'm going to now switch to the blackboard, but let me just flash the answer in case you want to sleep or leave or something. So the answer is that these functions psi m can be canonically decomposed into 2 functions, one of which is contains, so one of which we call the black hole partition function, the other one we call the multi-center black hole partition function. The black hole degeneracies are coefficients of this object, and the multi-centered degeneracies are coefficients of this. So this there's a unique way to do this, and the point is that this partition function of the isolated black hole is a mock Jacobi form. It should be. So I'll spend. So I think now I'm 45 minutes. Can we pull this up somehow? And I'll spend the next half an hour explaining. Thanks. So let's just switch this off, please. Oh, I'm only allowed to use this much? Ah, okay. Okay. Yeah?
Yes.
So, by the way, so everything I said so far in the classical modular form story is really classical, and if you want references, just look up one of the textbooks like the reference I gave. And what I'm going to say next is joint work with Atish Dabholkar and Don Zagier. So let's begin with what mock-modular forms are, because I think this will be used in other talks as well. So definition. So mock-modular form F. So I'll be brief here, but please ask me if it's not clear. Of weight k, which is either integer or half integer, is the first member of a pair of functions. So a mock-modular form is actually defined by two functions, f and g, where f of tau is a holomorphic function. Again, you can put some growth conditions to allow for exponential growth if you want. G of tau is a holomorphic modular form of weight 2 minus k, and G is called the shadow of F. And thirdly, f hat, which is defined to be f plus g star, I'll tell you in a minute what that is, transforms as a holomorphic modular form of weight k, and f hat is called the completion of f. Okay, and g star is a function that obeys the following equation. It's 4 pi tau 2 to the power k. Tau is tau 1 plus I tau 2. 4 pi tau 2 to the power k times dd tau bar of g star is equal to minus 2 pi I g of tau. Okay, so let me say again what this is. So g is some, so mock-modular form is a pair of functions f and g. Sometimes we just call f the mock-modular form, but this other function called the shadow, which is a holomorphic modular form of weight 2 minus k. F is not modular, but it can be completed into a modular form by adding a non-holomorphic function of g, and that non-holomorphic function is the solution to this differential equation.
Definition 3 should be f hat is a holomorphic modular form or non-holomorphic modular form?
F hat equal to f plus g star transforms as a holomorphic modular form of weight k. Let me emphasize this point. So so far I showed you that modular forms are holomorphic functions, but you have a larger space of functions which are real analytic modular forms. So one example is just eta times eta bar. That also has modular properties, right? But now you have a left and a right moving, left and a right weight, right? Half half. This function f hat is also real analytic. It's not holomorphic, but it transforms with weight k comma 0. So thanks. That's an important question.
K dependence on the property obeyed by G star?
Here.
Yeah, under K, K sequence.
Here.
Yeah.
So what's the question?
I thought
It's-
that was a star.
No, 4 pi tau 2 to the power k.
I'm sorry, it's my bad eyesight.
No, it's my bad handwriting. Okay.
G star uniquely, right?
Sorry?
This does not define G star uniquely.
How do you mean?
Well, you could add some holomorphic function of tau.
Yeah, so you can put some boundary condition to kill that. So there's an explicit, so let me, okay, so I didn't want to say this, but so you can integrate this equation, you can do it in many ways. Let me write the solution. Okay, so that's an explicit solution. It's called a non-holomorphic Eichler integral. If you give me a Fourier expansion of G, there's an even more explicit formula. This looks slightly analytic in terms of indefinite gamma functions. No, what is it called? The gamma incomplete gamma functions. Thank you. Incomplete gamma functions.
G is still holomorphic.
G is holomorphic.
Both F and G are holomorphic.
Both F and G are holomorphic. G star is not is real analytic, and it's sorry, here there's a bar, and the tau bar derivative of that is completely anti-holomorphic. Okay, so note that, so one comment, so suppose F is so F is a Mock-modular form, and some function H is a modular form, then F times H also obeys nice properties, namely tau 2 to some power here times dd tau bar of F hat times H is equal to H.
G star is not the same as G bar.
No. So G star is not the complex conjugate. G star is this function. It's a real analytic function of G. Thanks. Right. Yeah. So this, I don't know who chose this notation, but yeah. Not a physicist, clearly. Right. So. Sorry. It's antilinear in G, exactly. So, so if I have a Mock-modular form F with some shadow G and a regular modular form, you see that the product F hat times H also obeys a nice differential equation, H times G bar. Okay, so this you can generalize the class of nicely behaved.
G star is a function of tau and tau bar both, right?
Yes. G star is real analytic. Yeah. So that's, so here again. So F is holomorphic, G is holomorphic, and you complete F, which is equal to F hat is equal to F plus some real analytic function. So F hat loses holomorphy, but it has modularity. But the lack of holomorphy is given by this differential equation. So let me. That was the next point I want to make, that because F is holomorphic, you also have the same differential equation for F hat. Okay, so the point I was making here is that so you can now multiply modular forms with this. That's a larger class of functions. And then you can also take linear combinations of functions like that. So these have been called mixed Mock-modular forms and so on. But it's fairly obvious what they are. There is no classification theorem known. Okay, so and they do not form a ring. That's obvious from the definition. Yeah.
Sometimes one sees, I don't know if it's a definition or at least a property, that Mock-modular forms arise as the holomorphic part of harmonic mass forms.
Yeah.
Is that equivalent to this, or is it?
That's completely equivalent to this, right? But in fact, that's related to this comment. Once you start looking at slightly more complicated examples, it's very difficult to write. So this is not. If you want to ask now, suppose so mass form means that you have some Laplacian. So there's d tau bar and dd tau. But now if you hit dd tau, then it's also going to hit h, right? So it's not going to obey such a nice mass type equation. Right, so it might be some eigenfunction or something like that. So that's why this is a nice way to. The other, so people think of Mock-modular forms as that, and that's useful if you have analytic expressions. So in physics, sometimes it's useful because the mass forms might appear as the solution to some equation, or at some Poincare series or something like that. So it's completely equal. Okay. So the next thing is. I just remembered I'm being recorded, so I should be careful about my statements. Sorry? I can deny permission. I can just say that this segment should not be published. Okay.
Write up a good
Okay, so the next concept is mock Jacobi forms, and I started at 9:30 and something, 9:30 roughly, 9:30. Yeah,
20 minutes more.
it's 10:25 in my.
20 minutes more.
Yeah, 20 minutes, exactly. Good. So next concept is mock Jacobi forms. So just like we saw that for regular modular forms, a Jacobi form is the same as a vector valued modular form. You define mock Jacobi forms exactly like that. That it's a vector of mock modular forms, right? So you have phi tau z, weight k, index m. So let's call this mock Jacobi form. Is a mock Jacobi form if phi is holomorphic in both variables. Phi satisfies the elliptic property which is over there, and that means that phi of tau comma z can be written as L as a sum of L mod 2m of HL of tau times theta ml of tau z, exactly like before. But now you demand that HL of tau is a vector valued mock modular form. Okay, so that's the definition of a mock Jacobi form. That you write it. So you demand a holomorphicity in z and tau. You demand that it satisfies the elliptic property that implies the usual theta expansion, and then you have these coefficients, theta coefficients HL. When phi was a Jacobi form, these were modular forms, and now when this is a mock Jacobi form, this is a mock modular form. Okay, so that's sort of the obvious definition, so I won't say very much. So you can do the completion. You can define a completion called phi hat, which is equal to sum over L HL hat times theta ml of tau z. Okay, so these are vector valued mock modular forms with shadows GL of tau. Okay, so one general rule is whenever someone says that this function is a mock modular form, just look at the definition. The first question you should ask is, okay, what is the shadow of it? Because without that, it's not defined. Okay, so that's GL. So that's defined as HL. So it's defined as phi plus sum over L modulo 2m GL star of tau times theta ml of tau comma z. Okay. So that's the definition. Let me erase this. So let's look at some examples. Sorry? No, so I think it's supposed to be 3 things. Oh, I made it 4, but I guess that's okay. It's the whole doesn't burn. Okay, the whole word doesn't burn. Okay. Okay, so let's do examples. So essentially, so mock modular forms and mock Jacobi forms is a packaging problem. So I can present examples in one or the other. So the 0, which I won't say anything about because it involves a lot of it will take a lot of time. All of Ramanujan's examples fit into this definition. There are objects, there are numbers called Hurwitz-Kronecker class numbers, H of n, which, well, for any number theorists, is defined as the number of SL2Z equivalence classes of binary quadratic forms of discriminant minus n weighted by the reciprocal of the number of automorphisms. So if for physicists, actually we've seen this, that definition is not that difficult, just the number of solutions to a certain arithmetic equation. But essentially it's a set of numbers. The reason so there are a few reasons why I bring this example up. So the generating function, let's call it h of tau, which is sum h and q to the n. So h of 0 you have to just define to be minus 1 over 12, and then you have these other numbers, so minus 12, 1/3, 1/2, and so on. So they're rational, as I said. You can normalize it in any way you want. You can also, so this is a Mock-modular form of weight 3/2. Very good. Good. I was waiting for this. So I just began teaching last semester. So people passed on this trick to me that you shouldn't say everything, and this is how you see whether your audience is listening or not. I'll answer in a second. You can also make a mock Jacobi form, which is the following: sum of n of r h of 4n minus r square q to the n zeta to the r. And this is a mock Jacobi form of shadow sum L modulo 2 times theta 1 L tau 0 bar theta 1 L tau z. Okay. So knowing this, you can also compute the shadow of h because it's completely equivalent. In fact, the shadow is just the theta function, which is sum of q to the n square. Except that actually this mock-modular form is not a mock-modular form of the full SL2Z group, but on some congruent subgroup. So that's why I didn't. So this one is on SL2Z. It's a mock Jacobi form of weight 2 and index 1. And the place where physicists may have seen it is that this function is the what we call the Vafa-Witten partition function. So this is the partition function of SU2 n equal to 4 super Yang-Mills with SU2 gauge group in 4 dimensions on twisted on CP2. That's exactly. That's the first time it appeared in physics. Yeah, so that's an interesting question. I think that's still open. So in physics, we generally expect things to be modular because that's a symmetry. In this case, it's the duality of S-duality of n equal to 4 Yang-Mills. Vafa-Witten used some instant on counting arguments to compute the q, the coefficients of q to the n. It's actually h divided by e to the 6 or something like this. And then they said, well, this is not modular, and Zagier had understood what the modular properties are, and they just declared that it's the completion that should be the partition function. So no one has really understood that from yeah. The second example is again a construction.
So instead of the mock-modular form, it's a modular completion, which is the partition.
That's what one expects, because it's the partition function of Yang-Mills theory, and tau is 1 over g square plus I theta. So one expects, because of S duality, that it should be modular. You have to give up holomorphy. That still hasn't. That's an open problem as far as I know.
You also said it's not even the completion is not a very full line. Is that right? It's always
Yeah. So in this case, so this particular example is on some gamma 04, and so what I mean by that is that this is not modular. You can complete it to h hat, and that behaves like a holomorphic modular form on gamma 04.
okay. And is it understood physically why gamma 04 rather than SL2Z?
Yeah, that I think is understood. I mean, you can also see it from here. It's because there is. I have to recall the SU2 thing. So firstly, these two are exactly equivalent. So if you understand why it's index 1, you understand why that is gamma 04, because there are two. Because L goes from L can take two values.
Is it because the SU2 is not circular, or is that
That's probably right. So I have to remind myself of this. Yeah. But there's a way to understand. Yeah. Right. Hmm? Right.
I think partition function probably knows about that. This distinction between SU2 and SU3.
Okay, so let me go to.
SL2 doesn't transform as a vector. It's more. I mean, it's a two-dimensional vector.
Yeah, it's a two-dimensional vector.
Two-dimensional.
Yeah.
So that sounds then.
Yeah. So it's what is the it's so here. So this is. So here, this you can write as the usual theta expansion as h0 of tau theta 10 plus h1 of tau theta 11, and this h is I've combined h0 and h1, so it doesn't see it, but there's a vector of functions here. And the shadow is exactly this. There's two of them. Okay, so the next example is this construction which I call F22. The bottom two denotes the weight, and the top two actually denotes an index secretly. But this is an explicit construction. It's some r greater than s greater than 0, r minus s odd, minus 1 to the r, s times q to the rs over 2. So that has some q expansion. And from this, you build this function called h2, which is 24 times this f22 minus e2, the Eisenstein series at weight 2, which is not modular, divided by eta of tau cubed. And this function has the following q expansion, which many people in the audience know. So, and these numbers you will see again in some other talks. They also have to do with representations of the Mathieu group. This function is a Mock-modular form over SL2Z with shadow of weight 1/2 with shadow eta cube. And one can also make a Jacobi form, which is script F2 out of this, which is h2 of tau times theta 21 of tau z minus theta 23 of tau z, and that's a so F2 is a mock Jacobi form of weight 1, index 2, and shadow L modulo 4, sum L modulo 4 theta 2L prime theta tau 0 times theta 2L tau comma z, and prime means it's 1 over 2 pi I times d dz. Okay. This function also you may see in some of the lectures. Okay, so all these things I stated sort of without proof, but you can look at more explanations and proofs in the work with, I should have said the, I don't have the archive number. So this is work with Dabolkar and Zagir, so you can see explanations and proofs. Okay, I'll hurry. Okay, so can I take 10? No. That's exactly what I don't want to use. So the thing I want to sketch, at least briefly, is the problem that I presented, namely, and I want to do this because I think it will be used in at least some of the talks, at least one talk. Given some meromorphic Jacobi form, how do you write the Fourier expansion? And the message is that given some meromorphic Jacobi form, out comes a mock Jacobi form. Okay, so suppose phi. Yeah, I was just going to write that. So phi is meromorphic in Z. So this is exactly the black hole problem. So suppose phi is holomorphic in Z. So it's always holomorphic in tau. Then we've seen that phi of tau Z has this Fourier expansion. So this is, I'm recalling. Then we saw that there's a theta expansion. You could invert the theta expansion to get these coefficients, where now I'm being careful about the contour of integration. So all these formulas you already saw, and this is independent of Z naught. That's 3, and 4. H of L is vector valued modular. Okay, so this was a review of what I already showed you, right? If phi is holomorphic, suppose phi is a holomorphic Jacobi form, there's a Fourier series like this, there's a theta expansion like this. You can invert the theta expansion with some contour, but it's independent of the contour, and the answer HL of tau is a vector valued modular form. Suppose phi is meromorphic, then clearly this cannot hold because the right hand side is holomorphic. Okay. So now suppose it's meromorphic. This is also clearly not true, because if phi is meromorphic, if I move the contour, it's going to cross some poles and I'm going to pick up some residues, so it's not independent of Z0. This property relied on this property. I won't go into this, and this is also not true. It's a very easy thing. Basically, if you look at modular invariance, you have to prove modular invariance of this side, you should look at modular invariance of phi, and that also acts on Z, so it changes the contour. You'll have to pull back the contour. In the process, you'll pick up some poles. So that's also not correct. And in fact, even this is ambiguous. And as I'll just show you in a minute. So basically, nothing seems to work if phi is meromorphic. Okay. So now let me show you what to do. So first, let's try to understand why there's no Fourier expansion. There's no well-defined Fourier expansion. So suppose phi assume. So this is just for presentation. You can look at more complicated examples in the paper, but suppose phi has poles only at Z equal to 0 and its lattice translates. And also assume that the pole is of the following type. So near Z equal to 0, 1 by 2 pi Z plus order of 1, or 1 by 2 pi Z square plus order of 1. Okay. So in general, when you have a pole, you can have any order pole, and the coefficients in general are functions of tau. Okay. So I'm assuming for simplicity just the first two cases, and also that the coefficients are just 1. Okay. The coefficients you can make it 1 just by multiplying phi by some, or dividing phi by a modular form. So if I multiply this by a modular form, I can get whatever residue I want. And it turns out that the higher pole cases are essentially derivable from the first two cases. Okay. So now let's say, and now if you look at the transformations of Z, you will find that this has weight 1 and this has weight 2, because Z has weight -1. Good. So now let's look at the Fourier expansion. So suppose you have 1 over Z, or 1 over 2 pi Z. So we want, for Fourier expansion, we want to write things in terms of zeta, which is exponential of 2 pi Z. So use the fact that it's that, where as Z goes to 0. Okay. Now you write a Fourier expansion of this, but the Fourier expansion depends on the value of zeta, and it's equal to half plus n greater than 0 zeta to the n, or minus half plus n less than 0 zeta to the n, depending on whether modulus zeta is greater than 1 or less than 1 or greater than 1. So, in other words, if imaginary of z is greater than 0 or if imaginary of z is less than 0. So, the Fourier expansion is ambiguous, it depends on what value of z you are at. Okay. If you look at the Fourier coefficients, you will find something like this. So, when z is imaginary z is greater than 0, suppose this is imaginary z equal to 0, and then you have half 1 1 1 1, but when you go less it is minus 1 minus 1 minus 1 minus half 0 0 0. Okay. So, across this wall at imaginary z equal to 0, there is a jump of the Fourier coefficients. In this case the jump is constant, it is 1, but more generally it is not. Okay. The point is that there is a jump. You can do exactly the same thing for the double pole case, and just for use in the next 2 minutes, I am just going to define two functions, which is that, and similarly I am going to define something for the double pole. The double pole case is given by 1 over 1 minus zeta whole square. So, it is q to the m lambda square plus lambda zeta to the 2m lambda plus 1. Okay. So, what these functions are averages of this basic function which produces the wall crossing. So, there is this pole here, but that is just at z equal to 0, but we know that there is an ellipticity property, there is a periodicity property, and in order to do that I define these functions. So, these functions a1m, a2m are what are called Appel-Lerch sums. So, these were studied first by Appel and Lerch, I think in the 19th century. So, by construction, this is my last. Am I out of time? Exactly out of time? No, just to.
Yes.
Okay, so I'll finish very soon. So, by construction, these sums obey the ellipticity property with index m. Okay, thus I've averaged over the elliptic group. So, by construction. So, now I define one more thing. This is the final thing I need to define. So, suppose again I have phi a monomorphic Jacobi form of weight k and index m, and I just look at k equal to 1 or 2. I define HL of tau, which is a Fourier coefficient. I think so here remember that the Fourier coefficient depended on some contour. I am going to make a specific choice of contour, L tau over 2m minus L tau over 2m plus 1 phi times e to the minus 2 pi Lz dz. So, this is a specific choice of contour. Okay. But it is not a constant contour. The contour depends on L. Okay. So, if you make a constant contour, you will never get any modular properties, and this contour choice is actually inspired by the black hole attractor mechanism. And so, one thing you can very easily check is that defined like so, H is periodic with period 2m, HL is periodic with period 2m, and now define the finite part of phi to be the sum of HL times theta ml tau comma z L modulo 2m. So, this is periodic, so this is actually well defined, and also define the polar part to be a km for these cases. Okay. So, this is because of the assumption that the poles are simple. More generally, the polar part will be defined depending on the pole structure of the meromorphic Jacobi form. So, as I said here, if I assume that this is 1, remember that z under modular transformations z goes to z over c tau plus d. So, z has weight minus 1. So, they're the same. Okay, so with these definitions, the theorem with Dabolkar and Zagir is that with phi as above, which means that it's meromorphic with pole at z equals 0 plus z tau plus z, and it looks like this, 1 over 2 pi z to the power k, it's k equal to 1 or 2. So this is some restrictive version of the theorem. This is a much more general where you don't need, this can be at any rational point and so on. Phi is equal to phi f plus phi p, and secondly phi f is a mock Jacobi form of weight k, index m, meromorphic index m, with shadow. So it's going to be really the last thing I write. Prime bar theta ml tau 0 prime bar theta ml tau z, or theta ml tau 0 bar theta ml tau z, depending on the weights. So this k equal to 1 and k equal to 2. Okay, so that's the theorem. I'll stop in a minute. So the point of the theorem is that if you start with some meromorphic Jacobi form, you collect all the poles. So the meromorphic Jacobi form doesn't have a well-defined Fourier expansion. You collect all the poles into this function called phi p, the polar part of phi. You subtract that from phi to get something called the finite part, and that finite part is a mock Jacobi form. Right? So this is exactly what happens in the black hole case. You have some string partition function, the Dion partition function. There's a wall crossing function which is the polar part, which summarizes all the two-centered black holes. You subtract that, and as expected, we break modularity. But the fact is that you still have some vestige of modularity in that what you are left with, which is the single-centered black hole partition function, is a mock Jacobi form. Okay, I'll stop here. So there are things I didn't get to, for instance, applications of this theorem, and there are very nice examples, but we can talk about in discussion or privately. Thank you. So sorry for going over time a little bit.
Explain, let's say maybe a few more words about the relationship between specific contour that you use to define HL and the attractive mechanism.
Yes. So let me just. So remember, in this case, let me do it here. So remember that in this case, the partition function of Dions was this. So if you want to write a degeneracy, it's some contour integral something like this. Okay, it's a three-dimensional contour integral. Now this has zeros, so you need to specify what contour there is. And Cheng and Verlinde, actually Dabolkar and Nampuri, and then Cheng and Verlinde in the most general symmetric case, told you what the contour is, such that agrees with the spectrum of black holes in the gravitational theory. Right. So this is the microscopic partition function, but you also know what the spectrum of black holes is depending on the boundary conditions, depending on the moduli. So there's some set of moduli. So you figure out what this contour is depending on from the gravitational spectrum. So already it's pretty amazing that all the modular dependence is only in the contour and not in the partition function. This is not in general to be expected. It turns out that this contour is a function of both the moduli as well as the charges. Okay, so it's some it's here. Now, you know one thing for a fact, that when you impose the attractor, so if you make the moduli equal to the attractor moduli, then there is just no flow. You just go from infinity to the horizon of the black hole and the moduli don't change. So that's one region of moduli space where you know that you're bound to get only the single center black hole, because there's no splitting or anything. So if you say I fix this to be the attractor moduli, I will get the single center black hole. But what happens there is that all the moduli are fixed in terms of the charges. So attractor, which is single black hole, implies C is just a function of the charges. Right. So that's what happens in the string theory. Right. So the thing that we know, that the moduli dependence is fixed by the attractor mechanism, is determined completely by the charges, translates to the fact that the contour depends on the charges. And now you can translate this down to the Jacobi form picture by integrating out sigma, and you'll get exactly that the contour that I presented for the finite part is just the residue of this.
So I guess that tells you it doesn't depend on the moduli, but it doesn't tell you exactly what.
So there HL,
There's some more information you just
HL is right there.
so HL here. So it turns out that in this limit where you have only the Jacobi forms, where you expand in sigma at I infinity, this translates to the fact that this is q dot p. There's q square p square and q dot p in n equal to 4. And if I want L, then this is q. So basically the contour is specified by L. Right. So that was the inspiration. But just with this definition, you can check that HL, for instance, is periodic, and that HL is Mock, and
So does the black hole argument, so the black hole argument tells you the contour should be specified only by L, but does it tell you it's exactly this contour, or is it?
Yeah. So it tells, because you know what this function C is. You can even check that this is equal to this.
From the earlier.
From the Cheng and Verlinde prescription. So it just agrees with it on the nose, but now you can just throw away the black hole thing and just define this for any meromorphic Jacobi form. Yeah.
Yeah, so the black hole argument will also fix the sigma contour, right?
That's right.
Whereas you are taking the sigma goes to infinity.
Yeah. So you can. So for some values of charges, you can do this. So there's some, as you know very well, there's. That's right. So that's an assumption. So yeah.
So that you have to restrict probably m.
Exactly. So there's some n greater than m assumption.
That's exactly the relation. The n greater than m.
Yeah. Q square is greater than p square.
It doesn't involve L.
It doesn't. No, I think L should be either positive or negative. I forgot. And then. No. Yeah, that's right. At least when L is 0, it's just p square. But there's some explicit relation which we write down in the paper. So the statement about black holes is that the black hole degeneracy as a function of its charges is the coefficient of a Mock-modular form. The other way around is not true. So given these Mock-modular forms, it's not true that every Fourier coefficient is the degeneracy of one black hole. But this is also true even when there's no Mock behavior. Right? The polar coefficients are never black holes.
Sameer again for everything.
Thank you. Where is it?